Hey everyone, finally in this video we are going to implement our alpha-beta player and we are going to replace it with this random player here. So let's dive in. So before I start, I'm going to create this player class. Before I start, I should say that in the previous video I had included a link in the description. It was an explanation of the minimax and alpha-beta-pruning algorithms. And if you didn't watch that video, or if you are not familiar with those algorithms, I'm again including the link in the description of this video also. So make sure you first try to learn these algorithms, because as I told you earlier, I'm not going to explain the algorithms in detail. I'm only going to explain how to implement it in our situation in this chess game of ours. So being said that, let's go ahead and start coding our alpha-beta-pruning algorithm. So let's reuse this constructor and the decide move methods from the random player and change this with alpha-beta player, and we don't need this random object, and also constructor is undefined because we have to extend the chess player. So extends, okay. Alright, so now we are going to add our own decide move method here. So let's go ahead and first define a constant private static final int search depth. So let's go ahead and make this 5. Initially in this video we are going to use a constant search depth. So we are always going to search a tree of depth 5. This is a decent number because it's not too low. So 5 depth is actually enough for sensible moves, and it also isn't very high, so it shouldn't take too much time to compute the search. In the next video, actually, we are going to add a new feature called iterative deepening. But today, we are going to, as I said, use the 5 as a constant depth. Alright, so if you try to learn about this algorithm, you know that there is a maximizer and a minimizer. So let's go ahead and create those functions as well. Private int maximizer, and first let's add the arguments. So it will initially take in a depth, alpha, and beta. The minimizer similarly is going to take the same arguments. These two methods will be almost identical. We'll come back to that in a minute. But inside this decide move method, since we are not implementing this iterative deepening, it's very simple. We are only going to call the maximizer and then return the best move we've come up with so far. So best move. Of course, this has to be a field of our class. Private chess move best move. So this best move is going to be set inside this maximizer, of course, and the maximizer will take in the initial depth, alpha and beta values. So initial depth is this one, search depth, because we are here in the top node, in the highest level of our tree. So this means that we are 5 levels to search, left to search. And alpha is going to be integer min value, because we are going to maximize this alpha value, and it should start with a very low value, which is, according to the algorithm, it's a negative infinity value. And the beta value is integer max value, and that's, whoops, max value. That's the opposite of the alpha, so I mistyped something. This starts with positive infinity and alpha starts with negative infinity. And that's it. That's all our decide move method for now. And the meat of this video will be to implement the maximizer and minimizer. So let's start by the maximizer. The first thing we have to do here is to check the depth. So if you know about recursion, there are two parts. One, the recursion part. One, the return. So you have to stop somewhere, and this is the condition where you stop the recursion. So we are going to check the depth for that. If the depth is equal to 0, we can now return the base case. So the base case is the current board rating. So imagine a tree of depth 5. This means that we are at the bottommost level. So we are on the leaf nodes, and the leaf nodes should return the current state, the rating of the current state. So we can compute this by calling word compute rating, and the side should be black, because remember that this is our opponent, this is the black player, and the rating should be from the black player's point of view. And if the depth is larger than 0, now we should get a list of legal moves, because we can now we can still go down in our tree. So in order to go down, we should check our possible moves. Legal moves is equal to compute all legal moves. So let me remind you, this method is inside our base chess player class. So this will compute, iterate over all of our alive pieces and add up or accumulate all the legal moves that our chess pieces can make. And here we are getting that list. And then this is chess move, not moves. Alright, I accidentally closed it. Alright, so once we obtained this list, we are now going to try out each move inside this list, regardless of which level or which depth we are currently in. We are going to iterate over the chess moves. So chess move, legal moves. Alright, so this is where it begins to get a little bit tricky. So what we are going to do here is, first we are going to sequentially pick a move. So for example, the first element of this list, it's a chess move. So we are going to try this out by calling the makeMove method of our chess player class. And then we are going to let the minimizer, so the opponent, so here the minimizer corresponds to the user, so this is us. The alpha-beta algorithm will switch the side, so he will pretend like he is us by doing this. Side is side opposite. So now he thinks he is the white player now. Okay, so he is looking the game from our point of view, and then he should call the minimizer method and get a rating value. So minimizer. I'm going to fill these arguments, but let me continue here. So once he obtained the rating from one level lower, when the recursion is complete, then this actually returns a rating. Now he has to take back this whole thing so that he can evaluate the next move in this list. So he has to take back or revert the things he did here. So this can be done by calling the side opposite once again and calling the undo move method that we have created in the previous video. So this is where we are needing this. If you remember, in the last video we implemented this method, and the only purpose of this method is this one here. He has to undo this move so that he can go back up to the starting position to check the other legal moves. I hope this makes sense. And now this whole thing was to get a rating from the minimizer. So once this maximizer has got this rating, so I forgot to add the arguments. The arguments will be the depth, so this is identical with the maximizer, so the depth, but the depth will be one less because the minimizer now is one level lower than the maximizer, so we have to decrement it by one, and the alpha and beta will stay the same because they are somewhat global throughout this algorithm. And now once we have obtained this rating, inside this maximizer we are going to check whether this rating is larger than our alpha value. So remember, the objective of this maximizer is to maximize the alpha value. So if he sees a higher rating than the current alpha, he has to update this value with the new rating. So alpha is rating. And we have to do one additional thing here. So if you remember, we are keeping track of the best move globally. So here here is where we can update this best move, because we are in the maximizer, and if we came across a better alpha, and also if we are in the base, the topmost layer, so we're in the first node, the recursion went down and went back up to the topmost node. So we can check this by its depth equal to search depth, and then if that's the case, we can update our best move. The best move is move. Now this was the minimax algorithm so far here. Now we'll add something else to implement actually the alpha-beta pruning, not just minimax. So if we are going to check if the alpha is greater than or equal to the beta value, then this means, according to this algorithm, this means that you no longer have to search for the other branches. You can just prune them. So you can just exit or break this for loop. And we're going to break this loop by returning the current alpha simply. Again, this is assuming that you know about the alpha-beta pruning algorithm. And that's it for the maximizer. We only forgot to return alpha. So the main quest of the method is to return, maximize and return this alpha value. And if you understood this method, the maximizer, the minimizer is actually very simple because it's almost identical. So we can actually copy all this stuff because the difference is here. Instead of alpha, the minimizer will try to optimize or minimize the beta here. So let's paste that. And let's not forget to change this to maximizer, because they will call each other. So the difference starts here. So we checked the rating is larger than alpha in the maximizer. In the minimizer, we are going to check if the rating is smaller than or equal to the beta value. Did I mistype it? Rating. Alright, I have to put this inside the for loop. Alright, so if the rating is smaller than beta, now we are going to update the beta. This is because the minimizer is trying to minimize this beta value. And we're not going to do this because remember that the minimizer is the opponent. You can only select the best move if you are on the topmost node, and the topmost node is a maximizer node in the tree. So again, this is so far the minimax algorithm, and here we can check the pruning if we can prune any branches. So we're again going to check alpha is greater or equal than or equal to the beta, and if that's the case, return beta, because whenever alpha is greater than beta, you no longer have to search the other branches. And that's it. Finally, let's return beta here. And if I didn't mess anything up, this is our alpha-beta pruning algorithm. I know it's not very explanatory, but as I said, it will take a very long time for me to explain the algorithm to you. And also there are very nice explanations on YouTube or other resources. So you are better off learning from those instead of me. And let's go ahead and try out our new player class. But before that, we have to update our chess room, because at the moment we are creating a random player for the black side. So let's comment this out and make this alpha beta player. So let's launch our program. So let me tell you that I'm not a great chess player. Actually, I'm not at all into chess, but I'm going to try to make sensible moves so that we can try out our algorithm if he is good or not. So let's do that. Oops. So I told you that I'm not a good player. He captured my pawn, and actually, as you see, he's in a very nice position here. He's not greedily capturing a pawn just because he can. I have no way to capture this bishop now. So I cannot fully. So he is threatening my queen now. I cannot fully test this. I have to play a full game, and it will take very long. But you can go ahead and test this, and if you notice any bugs or something I did wrong, feel free to tell me about it. I'm going to stop this now, and in the next video we are going to add this iterative deepening feature to our alpha-beta player class, and it will be a much harder opponent, tougher opponent once we do that. So see you in the next video. Take care.